Hello students, myself Rahul Kotkar. In this lecture, we are going to study about the chapter Magnetic Fields Due to Electric Current. It's our lecture number 5. Which topic we have to study in this lecture? It's our 10.11, that is force of attraction between two long parallel wires. Okay, so means what we have to consider, the two long parallel straight current carrying conductors. Okay, understood? Means what we are going to consider, two long straight parallel current carrying conductors. These conductors, these conductors are simply like this. These are the two long straight parallel current carrying conductor. First case that we are going to study here, that is both are carrying a current in the same direction. Means I1 be the current flowing through the first conductor and I2 be the current flowing through the second conductor. Both are separated by a distance say as to d. Okay, so what we have to study here, we have to calculate or we have to find out the force of attraction or force of repulsion between these two conductors when they carries a current in the same direction as well as in the opposite direction. So let's start with this topic. Okay, so first thing, while considering this topic, I am representing you a simple figures. So you can observe this figure. This figure shows you. In this figure, what we observe, these are the two long straight parallel current carrying conductors. So this particular long straight carrying conductors say as to 1 number, 2 number, carrying current I1, carrying current I2. Now, when the current flowing through the conductor 1, so we know that when a current flowing through a conductor, it produces the magnetic field around it. Means what? The second conductor experiences the magnetic field of the first conductor. Okay? So, what is the magnetic field produced by this one? So, let me consider that as per the right hand rule. Okay, what we can say, okay, means you have to apply here right hand rule for this conductor. So as you apply the right hand rule to this conductor, so what you can say, the magnetic field produced on the second conductor having a direction in the downward direction, say as to like this. What is this? Magnetic field experienced by the conductor 2 but due to 1. So I will represent this magnetic field as a B1. Understood what I say? When a current carrying conductor 1 carries a current through it, at that time the conductor 2 experiences the magnetic field due to the first. Okay, so by applying right hand thumb rule here to this conductor 1, what we can say? We say that the magnetic field produced on this conductor 2 or conductor 2 experiences the magnetic field due to the first, and that is represented as a B1. Now, what is the magnitude of this one? So, the magnitude of this one is simple. B1 is equal to mu 0 I divided by 2 pi d. Okay, where d be the distance. Here represented as a but we consider as a d. Okay, this figure is only for reference for you. Okay, so what is this? B1 is equal to mu 0 I divided by 2 pi d. This must be the value of this magnetic field. That is the magnitude of magnetic field experienced by conductor 2 due to conductor 1. So, in similar manner, okay, now this about only the magnitude. Now what? The magnetic field is the vector quantity, so it have a both magnitude as well as direction. What about its direction? I am representing it by a downward arrow, but why this downward arrow is there? So apply the right hand thumb rule. Okay, you just consider that this conductor 1 is held in your right hand in such a way that, okay, is held in your right hand in such a way that the finger are curled and thumb is stretched. The stretched thumb denotes the direction of current flowing through it. What is that? The stretched thumb denotes the direction of current flowing through the conductor, and curl fingers shows the direction of magnetic field. So friends, just imagine you held the conductor in such a way that, okay, the thumb represents the flow of current and curl finger represents the magnetic field. So in such a way that your palm is in the downward direction, means your palm facing in the facing towards the ground. So held the conductor like that. What do you observe? Your fingers are curled in a downward direction. So this is what? This is the direction of magnetic field produced by conductor 1. Okay. Now what we have, as we find here, the magnetic field produced due to the conductor 1 is B1, and now the current flowing through this conductor is I2. Okay, I am again drawing this figure once more. Okay, simple. What is that? Okay, so this is your current I1, current I2, the second conductor, first conductor. Now we just observe that this is the magnetic field produced by the conductor 1, okay, experienced by conductor 2. Now what you have? You have a simple, this is the direction of flow of current I2, this is the direction of magnetic field. Means here what you observe? You observe here the magnetic field as well as current, both are experienced by the conductor. Means it's the case where what we observe? A current carrying conductor kept in a magnetic field. Okay, so this is the current carrying conductor kept in a magnetic field, experiences the force. So how we can calculate this force? So to calculate this force, we have to use the Fleming's left hand rule. Okay, that is a Lorentz force law also. Okay, so what is this Fleming's left hand rule? And according to that, what we can say? We simply say that stretch the three fingers, okay, that is thumb, middle finger and forefinger of the left hand in such a way that they are mutually perpendicular to each other. Okay, so forefinger, okay, means in between the thumb and middle finger, the forefinger represents the direction of flow of current. Okay, it represents the direction of flow of current. Then what we can say, there is a mistake. The forefinger represents the direction of magnetic field. Okay, and middle finger represents the direction of flow of current. Okay, it's simple like this. Forefinger represents the direction of, okay, this is your forefinger. Then this is the direction of current by middle finger. Then thumb shows you the direction of force experienced by the conductor. And so what we can say here, the direction of force is directed toward conductor 1, that is F2. Okay, you can see this one, F2. Okay, means what? This, in the presence of current I2 and magnetic field B1, the force experienced by conductor 2 is directed towards conductor 1, and that is simply represented by F2. This is what? Direction. Now what about the magnitude? As similar to the magnetic field, we have to find the value of magnitude. Okay, so what is that? Simple. F2 is equal to I2 means current multiplied by magnetic field. Okay, so simply what we can write here, F is equals to I into L into B. Okay, we have this formula. And according to that formula, what we can write? So F, current is what? Basic current flowing through this circuit is, conductor is I2. Length of the conductor, let's suppose it should be the L. Okay, and what is this B? B be the magnetic field induction. Okay, so that is mu 0 I1 2 pi D. Okay, and so in this manner, finally, we got a formula that is simply your F2 is equal to mu 0 2 pi, okay, mu 0 2 pi I1 into I2 divided by D, okay, into L. L be the length of the conductor, okay. But mostly what we are considering, we consider the forced acting per unit length, okay. So I will erase it again. Mostly what we are considering, this is the formula for F2 is equals to I into L into B. What is the current flowing through the conductor? I2. So it is I2. Okay, this is the magnetic field experienced by this conductor is B1. Okay, so therefore L multiplied by B1 is what? Mu 0 upon 2 pi I1, okay, divided by D. So what is our formula? Mu 0 divided by 2 pi I1 I2 divided by D. Okay, and now this L again remains. But mostly, okay, formula is considered as a forced acting per unit length, F2 divided by L. So this L comes here, and in your book it is represented as a F dash. Okay, what is that? Forced per unit length of the wire. Understood? So in this manner, what we found? We found that the magnetic field B1, we found the value of magnitude as well as direction of force experienced by first conductor or force experienced due to the magnetic field B1 and current I2. Okay. In similar manner, what we can say? In similar manner, we can say about, in this case, okay, we just observe that this is the force F2, this is the magnetic field B1, and this is the current I2. Okay. Now, in similar manner, what happens? This conductor carries the current I2. So, as it carries the current I2, so again what we have to consider? We have to consider that when it carries the current I2 from this conductor 2, so at that time it experiences the magnetic field. Means magnetic field produced by second conductor and which is experienced by first conductor. As it is experienced by first conductor, so what we can say, the magnitude of this one, we called it as a B2 because this is the magnetic field due to the second conductor. Okay, so what is the value? Value is simply your, as similar to the previous formula, mu 0 I2, current is I2, 2 pi divided by into D. Okay, means what? This is a D with the distance between these two parallel conductors. Okay, now in this case, this is your magnitude. Now, what is the direction of this magnetic field? To find the direction of magnetic field, what we have to use? Simply, we have to use the right hand thumb formula. Again, as you apply the right hand thumb formula and apply that formula in such a way that imagine the conductor 2 is held in your right hand in such a way that the thumb shows the direction of flow of current, means this one I1. Thumb shows, current I2. Thumb shows the direction of flow of current I2 from conductor 2. Okay, and the fingers are curled which shows the direction of magnetic field produced. So you have to held or you have to imagine held your hand in such a way that the conductor is held in your hand and your palm is facing towards your face or at the roof. Okay, and at that time you will consider what is that the stretched thumb shows the direction of flow of current while the curl finger shows the direction of magnetic field. Means the direction of magnetic field is simply like this. okay, in the upward direction. So B2 be the direction of magnitude of the magnetic field is this one, okay, and direction is upward, okay, means outwardly directed. So friends, in this manner we obtained the magnitude as well as direction of a magnetic field produced by the second conductor and experienced by the first conductor. Okay, remember the words what I am using. Okay, then same thing again, this is the magnetic field B2, current carrying conductor I1, means current flowing through the conductor is I1, means the conductor carrying current kept in a magnetic field experiences the force. Again, what we have to use? You have to use the same formula. What is that? Force F2, force to the first conductor, that is F1, this one, okay. So F1 can be given by F1 can be given by I into L into B. For conductor 1, current flowing through is I1, magnetic field is B2, okay, this one. Means again your formula is I1, L remains as it is. What is the B2? That is mu 0 I2 divided by 2 pi D. Again this L goes here, okay, and what becomes? It is a force acting per unit length. Okay, so friends, what you observe in this case, you just simply say that force acting per unit length is equals to mu 0 I1 I2 divided by 2 pi D. Okay, this is for the conductor 1, and the direction of this one again given by what? Fleming's left hand rule. As applying the Fleming's left hand rule, what we have? The forefinger shows the direction of magnetic field, middle finger shows the direction of current, and the magnetic field, the force is nothing but directed towards the conductor 2. Okay, and so in this manner what we can say, the both forces force F1 and force F2 both are directed towards each other. Okay, means they directed towards each other, means what we can say? We say that they are attractive forces. Okay, they are what? Parallel currents. Okay, in case of parallel currents you may say as a like currents. In this case they attracts each other, means these two parallel conductors attracts each other because of what? The force directed towards each other. One more thing that we have to observe here and focus here, what is that? The force acting per unit length for first conductor and force acting per unit length for the second conductor, both are equal in a magnitude. Okay, as you cancel the length, okay, both parameters get cancelled. What you can say? In a magnitude, F1 is equal to F2, means both forces are equal because the length of the conductor is same, direction of flow of current is same. Okay, in that case what happens? They should be the equal. Again, one more thing, okay, means you have a formula simply like this: force acting per unit length is equal to mu 0 upon 2 pi into I1 I2 divided by D. But when you consider the magnitude, okay, direction, so you can write this one, F1 is equal to F2, but there should be the negative sign. Okay, because both forces are opposite in direction. Okay, means one is towards the left side, you may call, and other is towards the right side, and so they are opposite in direction. Their direction is opposite, but what? They have a equal in a magnitude. So we talk here, or we discuss here only about what? For a like currents. Okay, there is a simple sentence given to you. We can summarize this like a result: parallel currents attracts and anti-parallel currents repel. So what is the about anti-parallel current? This totally about what? Parallel, or you may call a like current. Okay, not a light, it is a like current. Okay, like means in the same direction. So friends, in similar manner we have to discuss about unlike current, that is anti-parallel. Actually in the syllabus that is not given you in a briefly, okay. So we talk here by a simple way using this figure only. So you can observe this figure and just apply, okay. I am just summarize the previous topic and also explain this topic, okay, for unlike current. Means both things will be conducted here simultaneously. So first thing, let we consider these two current carrying conductors which are parallel to each other, okay. Now there should be the unlike current. Current, suppose I1 is directed towards your side and I2 is directed in the away from you, okay. Both are separated by a distance d. Now you have to just imagine that by applying the right hand thumb rule. First you have to what? Apply the right hand thumb rule for conductor 1, okay. As you apply the right hand thumb rule, so what you observe, held your right hand in such a way that the thumb shows the direction of flow of current and curl finger shows the direction of magnetic field, okay. Held your right hand in such a way that the palm is facing towards you or roof, okay. So in that manner what you can say, the direction of magnetic field is upwardly directed, that is B1, okay. Now second thing, when same thing again, what we have to explain here, this is the direction of magnetic field, this is the direction of flow of current, means the conductor carrying a current kept in a magnetic field and so it experiences the force. Again for that you have to apply Fleming's left hand rule, and according to that what we can say, the direction should be like this, that is what, due to the second conductor, and so it is a F2, okay. Now again same procedure you have to follow, okay. You can write the magnitude of all these one, B1 as well as B2, B1 as well as F2. Second thing, now again repeat the same procedure for the conductor 1. So as a conductor conductor 2 carrying a current I2, as it carries the current I2, so what you can say, the conductor 1 experiences the force. Conductor 1 experiences the force. As conductor 1 experiences the force, initially it experiences the magnetic field. What is the direction of magnetic field? Again apply simply the Fleming's right hand thumb rule. According to that, what do you have? Okay, when a current flows in this direction, so this is a direction of flow of current. Held your right hand in such a way that, okay, the direction, your palm facing towards the upward side, and so what is that? The direction of magnetic field is B2, which looks like this. So again what? This is the direction of flow of current, magnetic field B2. So what is this? This is the force experience. What is that? F1. So what you observe, F1 and F2 are moving away from each other, okay. Means this is the unlike current traveling in opposite direction, moving in opposite direction, and in that case what we can say, the F1 and F2 are directed in the opposite side, okay. And so what we can say, there is the repulsion between the two parallel conductors, okay, carrying a current in the opposite direction. Understood what I say? It's a simple case. In this case what we can say, okay, you have in your book there is only a simple sentence, anti-parallel currents repel, but why they repels? According to this figure, okay. Mathematically you can represent the same value, no change at all, okay. Just there is a change in direction, and so I will just focus about the direction, okay. So you can say here both forces are moving away from each other, and that's why what we can say, the two parallel conductors carrying unlike currents or opposite currents or anti-parallel currents, there should be the repulsion. And in case of parallel currents, means current moving in the same direction, there is the attraction. Remember, these are the two noteworthy points. Okay, understood? Okay, then after this topic, we have to study a simple definition of ampere. Okay, which definitions we have to study? Definition of ampere. Okay, everyone know what is the ampere? Ampere is the unit of current. Okay, means it is a SI unit of electric current. So what do you mean by 1 ampere? So for that you have to consider the two long straight parallel conductors carrying current I1 and I2. Okay, separated by a distance say as to D. Remember, these two conductors are kept parallel, carrying current I1 and I2 respectively. Okay. Then, if suppose there may be possibility that these two currents carrying a current in the like direction, either in the unlike direction, means the current flowing through it may be in the same direction. Okay, that is a parallel or anti-parallel. Okay, and so for that there may be the force of attraction or force of repulsion. In your book there is only the word used here. Okay, the force of attraction. But at actual, what we can say, there may be possibility of what? Force of attraction or force of repulsion. Okay. So let here, according to that, there may be the attraction, there may be the repulsion. Okay, depends upon the direction of flow of current. Now we have a formula, force acting per unit length is equal to mu 0 divided by 2 pi I1 I2 divided by D. Okay, now listen here, let me consider that the current flowing through each conductor is of value of 1 ampere. Suppose, means current flowing through the first conductor is also 1 ampere, I1 having value 1 ampere and I2 also having value of 1 ampere. The separation between these two conductors is said to be of 1 meter. How much the difference? How much the distance between two parallel conductors is 1 meter. Okay. Then by substituting the value, okay, listen here, F upon L, this formula we just wrote here. F upon L is equal to mu 0 upon 4 pi. Everyone know the value of mu 0. What is the value of mu 0 upon 2 pi? Okay, first I will write there mu 0 4 pi into 10 to the power minus 7 divided by this is 2 pi as it is. Okay, into, as just I told you, the value of current I1 and current I2 flowing through the conductors is what? 1 ampere each. So 1 ampere multiplied by 1 ampere is 1 ampere. Divided by distance of separation is what? Distance of separation between these two conductors is 1 meter. Okay, and now what is the formula value we got? Pi get cancelled, 2 get cancelled, 2 multiplied by 10 to the power minus 7. Okay, force, so Newton, and length for meter. Okay, so force acting per unit length is 2 into 10 to the power minus 7 Newton per meter is what? The force of attraction per unit attraction or repulsion per unit length on a conductor. Okay, so how we can define the ampere? Now question is that how we can define ampere. So everyone got the value 2 into 10 to the power minus 7. How it should become? It should become using a simple consideration. The current flowing through the conductor is said to be of each of 1 ampere. Okay, and the two conductors are kept parallel to each other at a distance of 1 meter. And the value of force acting per unit length is 2 into 10 to the power minus 7. Okay, now again to define it, let's just how the ampere is defined. Here the definition given to you is completely different that I am going to explain. Okay, but the meaning is same. and I think it should be very simple. Okay, so what is that? When a two parallel, just focus what I am saying, when two long straight parallel conductors carrying a current I1 I2, okay, carrying a current of 1 ampere each. Okay, listen carefully. When two long straight current carrying parallel conductors carrying a current of 1 ampere each, separated by a distance of 1 meter, then the force of attraction or repulsion per unit length between them is equals to 2 into 10 to the power minus 7 Newton per meter. Then the current flowing through the two conductors is said to be of 1 ampere each. Okay, understood? What is the definition? Simple. I am repeat it again. When a two long straight parallel current carrying conductor carrying a current of 1 ampere each from each conductor, separated by a distance of 1 meter, then the force acting per unit length, okay, it may be the force of attraction or repulsion, force acting per unit length is equals to the 2 into 10 to the power minus 7 Newton per meter. Then the conductor carrying a current is said to be of 1 ampere each. Okay, understood? The current flowing through each conductor is of 1 ampere. Under this situation, it produces the force per unit length is equals to 2 into 10 to the power minus 7 Newton per meter. So in this manner, we studied about what? Force of attraction between two long straight parallel conductors. Okay, there for like current means parallel currents as well as anti-parallel currents or opposite currents, that is unlike current. Understood, friends? Okay, now